this video is going to be all about what a tangent line is, how to find the slope at a specific point, and then eventually we'll learn the term derivative, which is what instantaneous rate of change is, which is finding the slope at a particular point or finding the slope of a tangent line at a point. All those mean the same thing, and we'll get into it little by little. But basically, what we're going to be doing here is if we had a straight line, you can find the slope of that line simply by doing rise over run, or change in y over change in x. That's the slope. And lines always have constant slope. So how do we find the slope when we have something that's not a line, where the slope is not consistent? That's our big problem that we're solving with using calculus. So for this parabola, at no 2 points on this graph is the slope exactly the same. It's constantly changing. For example, if I took the slope right here, if I zoomed in and took the slope right at that point, I would have a slightly positive slope because our graph is increasing right there. But if I moved further up on the graph, my slope is going to become even more positive because it's getting steeper. And then further up on the graph, it's going to become an even bigger positive number. All of those points have a slightly different slope at them. What the graph is doing at a particular point, we call that like being tangent to the graph. Like if you can imagine a slope at that. So drawing a tangent line would be like if I were trying to draw the slope of what's happening at this first, we'll go back to that first particular point. Then I know it's going to be slightly positive. Whereas at the next point, it's going to be still positive, but a little steeper. That's not a great line. I'm actually pretty bad at this. And then the next one, it's going to be even steeper. Like I said, really bad at this. Whereas on the other side of the graph, they're all going to be negative points. Now, what I could do on this graph using what we know so far, we could find what's called the average rate of change between 2 points. Like if I wanted to find the average rate of change from 0.31 to 0.67, I'm just choosing 2 good points here. If I wanted to find the average rate of change between those 2 points, and it's basically like drawing a straight line through those 2 points. That's called a secant line. And we are going to find the slope of that secant line. And to do that, we just do change in y over change in x. So 7 minus 1 over 6 minus 3. So the average rate of change between those 2 points would be 2. If I were further down on the graph, my instantaneous rate of change, or my slope at that particular point, is going to be less steep than 2. But if I come up here, my instantaneous rate of change is going to be more than 2. But our average on that interval, like even over here, it's going to be more than 2. But our average on that interval is 2. So let's practice with instantaneous rate of change for a second. So if we have a function, here's my function, and I want to find instantaneous rate of change over the interval 1 to 3, I'm finding the slope of the secant line from 1 to 3. The 1 to 3, those are talking about your x values. We need to find the corresponding y values by plugging those back into the function. So I know f of 1, when I plug that into the function, I get 1 minus 3. And when I plug 3 into the function, I get 27 minus 9. So if I'm finding the average rate of change, and we use AROC a lot for average rate of change, AROC. The average rate of change is the same thing as the slope of the secant line. So if you were just to draw a straight line between those 2 points, and our change in y over our change in x would be 18 minus negative 2 over 3 minus 1, or 20 over 2, which is 10. Our average rate of change between those 2 points is 10. This is the more formal version equation for the slope of a secant line, f of b minus f of a over b minus a. And that might be a little bit more helpful when we go on to talk about how to find the slope of a tangent line. So again, the difference between a secant line and a tangent line. Secant line connects 2 points. Tangent line is what is the slope of the graph doing at one particular point. So like at point P. So like for this quadratic, up at the top of this slide, the slope of the tangent line is less steep than the slope of the secant line. Or we would say the instantaneous rate of change, the slope of the tangent line, is less than the average rate of change, the slope of the secant line. So how do we find, using our slope formula, our average rate of change formula, which is f of b minus f of a over b minus a, how do we use that to help us find out the slope of a tangent line, so the slope at one particular point? So to do that, we are going to have point A, that's the point that we want to find the slope of the tangent line on. And then we're going to add on this point. It says h, but it's really going to be a plus h. Let me put that in there. A plus h. So we're basically adding just a little bit to A and then finding the slope between those 2 points. And the further I move closer to A, so the difference between A and A plus H is H. The closer I move that A plus H to A, the more accurate my instantaneous rate of change is. Because again, instantaneous rate of change is the slope of the tangent line. It's what is the slope doing right at that point. And so the closer I move that second point to A when I use the slope formula, the closer that will model the slope of the tangent line. So our average rate of change between this point A and this arbitrary point A plus H would look like this. We'd have f of A plus H, that's the y value of the second point, minus f of A, that's the y value of the first point at A, over A plus H, that's my second x value, minus A, that was my first A value, or x value. And I could simplify this just a little bit further by, in the denominator, the A and the negative A cancel out, and we're just left with H. So that's finding the average rate of change between 2 points where that H is just a little tiny amount. The smaller H is, the closer we are to modeling the slope of the tangent line. So the slope of the tangent line is the limit as H approaches 0. We want the distance between the 2 points to be approaching 0. It can't be 0 because if there's no distance between 2 points and we try to take the slope of the line, like if I have the point 1, 3, and I want no distance between my 2 points, that means my second point is also 1, 3. And if I try to take the slope of that line, I get 3 minus 3 over 1 minus 1, which is 0 over 0. That's indeterminate form. We can't do that. So we're going to do this, the limit as H approaches 0. We want that distance to become smaller and smaller and smaller. And this is what we're going to use now to find the slope of the tangent line. So this is for finding the slope of the tangent line, which is instantaneous rate of change. All of those things mean the same thing. And later we'll also call it the derivative. By the way, this equation right here is called the difference quotient. So if you see things mentioned as that's not how you spell difference, as the difference quotient, this is what they're talking about. All right, so before we practice using the difference quotient, let's practice finding f of a and f of a plus h, because those are two things we need in order to use the difference quotient. So anytime you see f of a, you're basically plugging a in wherever there's an x. Later, that letter A will become a number like f of 3, and we'll plug in 3 for x. But for right now, even later in this video, it becomes a number. But for right now, we're just going to leave it A. So f of A, instead of 1 over 2x, would be 1 over 2a. For f of a plus h, we'd have 1 over 2. Where the x is, we're going to substitute a plus h. Really important to put it in parentheses because we need to multiply both of those by 2. Second example, f of a, we are simply substituting a where the x is. Later, again, that a will be a number instead. For f of a plus h, we are substituting a plus h where that x is. So we're going to use those skills now to practice using the difference quotient to find the slope of the curve at a point. When we are finding the slope at a point, we are finding the slope of the tangent line or instantaneous rate of change. And again, later we're going to call that the derivative or the slope of the derivative. Here we go. So let me write down that difference quotient just so we don't forget. So it's the limit as h approaches 0 of f of a plus h minus f of a all over a plus h minus a, which is h. And that just comes from our basic slope formula, y minus y over x minus x, our change in y over our change in x. So in this case, our function is x squared. So when we plug in a plus h for x squared, that's going to become a plus h squared. And then we're going to plug in a all over h. So the reason we need to do this at all, again, if typically the first thing we do when we're trying to find a limit and we're approaching a number is we try plugging in that number. But when we try plugging in 0, we're going to end up with 0 over 0, which is indeterminate form. So now I need to simplify this just like we practiced in Unit 1. So simplifying this, and we can't lose our limit, I get a squared plus 2ah plus h squared minus a squared all over h. The a squareds cancel out. And so now I can pull out an h. We're getting close. And I get 2a plus h over h. Or 2a plus h. So now when I plug in 0 for h, I do not get 0 over 0. I get 2a. So our answer in this case would be, or the derivative, we've got 2a. And because we want it at the at 3, 9, at the point 3, 9, 3 dots means therefore, by the way. Therefore, at the point 3, 9, that means our a is 3. We're going to substitute 3 in there, and we get a slope of 6. So our slope in general for this function is 2a. If we would have wanted to find the slope at 2, 4, we would have plugged in 2 for a, and we would have gotten 8. Wait, no. 2 times 2 is 4. We would have gotten 4. So at the point 2, 4, our slope would have been 4. At the point 3, 9, our slope is 6 because we plug in a 3 for a instead. So then a follow-up question is to, or follow-up prompt is to write an equation of the tangent line. So we know from Algebra 1 that to write an equation of a line, we need 2 things. We need the slope and we need the point. Well, we have the slope now. We found out that at 0.39, the slope is 6. So we also have the point. The point is 39. So let's imagine this for a second. We have the graph x squared, which is the parent function of a parabola. What we're saying is that at the point 39, if I draw the tangent line right there, that slope of that tangent line is 6. So now in this next example, it wants us to write an equation for that tangent line. Well, we know the slope of that tangent line is 6, and we know it goes to the point 39 because that's the point that we're drawing the tangent line at. So now we're going to use point slope form, which if you remember from Algebra 1 is y minus y1 equals m times x, minus x1. And we're going to substitute in our values. And that's it. Let's try that for another example. One more example. So I'm going to jot down that difference quotient again. It's the limit as h approaches 0 of f of a plus h minus f of a all over h. So first I'm going to plug in a plus h into this function. So where the x is, I'm going to plug in a plus h. A represents the x value. Or later, just x. It will represent just x. Now I'm going to just substitute a. And then all over h. Now this one's tricky because we've got a complex fraction. We have fractions within fractions here. And to get rid of fractions within fractions, we need to multiply everything by the common denominator. The common denominator in this case, we have two different denominators. Our first denominator is a plus h plus 3, and our second one is a plus 3. So we have to multiply by both of those. To get a common denominator, you cannot just add h to the second one. It always has to be multiplication, not adding and subtracting. So when I multiply this all out, it's going to get a little bit messy. Not too bad, actually. So when I multiply this first fraction by all that, the a plus h plus 3 will cancel out, and I'll be left with a plus 3. When I multiply the second piece, I'm going to get a plus h plus 3, because the a plus 3's will cancel out. And in the denominator, I have h, a plus h plus 3, and a plus 3. I'm not going to multiply that out. That will overcomplicate things. Now in my numerator, I'm going to simplify that a bit. The a's will cancel out. I'll have a minus a. The 3's will cancel out. I'll have 3 minus 3. And so what's going to be left is a negative h over h times a plus h plus 3 times a plus 3. Now the a's are going to, the h's will cancel out. The h's should always cancel out because when we plug in this 0, we should never get a 0 in the denominator. If we do, the limit doesn't exist there. But in most cases, we should get something nice here. So now I'm going to plug in a 0 for all my h's. And so I have a negative 1 in the numerator. This h is going to go to 0. And so I have a plus 3 times a plus 3 in the denominator, or a plus 3 squared. I feel like there was a follow-up question in the notes on this. Yes, so then the follow-up question. So this is our general slope formula. That's to find the slope at any point on that graph of f. And then the follow-up question says, find the slope of the curve at x equals negative 1. Let me use a different color. So at x equals negative 1, we're going to plug in a negative 1 for a. So the slope at that tangent line will be negative 1 over 2 squared, which is negative 1/4. So that's the slope at our tangent line at negative 1. And then it says write an equation of the tangent line to that curve. So 2 things we need to write an equation of a tangent line. We need the slope, which we just found. It's -1/4. And we need the point. Well, we know the x value is -1. To find the y value, we need to plug that into f of x. So plugging in -1 into f of x, we end up getting 1/2. So with the slope and the point, we can write our equation, y minus 1/2 equals -1/4 x plus 1. That's our slope of the tangent line. Second follow-up question says find the slope of the normal line. This is our last vocab word for this lesson. Or it says write an equation of the normal line, sorry. Normal lines are always perpendicular to tangent lines. So what we know about perpendicular slopes is that they're opposite reciprocals. So if our slope of our tangent line was -1/4, the slope of our normal line will be +4. That's really all you need to know about normal lines. They are perpendicular to the tangent line. So it's going to go through the same point, but the slope will be opposite reciprocal. So that's the equation of the normal line. The main thing we're adding in the next lesson is the word derivative, which is the same thing as the slope of the tangent line or instantaneous rate of change. We've got the same formula. Notice that this is our difference quotient. It's just instead of a, there are x's because our derivative function is typically a function or always a function of the original function. And we use this notation f prime of x. That's what you'll see used the most. However, there are multiple other ways you can see it written. All of these mean the same thing. So just kind of become familiar with that notation. These top 3, I would say we use the most. But f prime of x means the derivative of f at x. Y prime is just kind of like a shorthand way of writing the same thing, or dy dx means the derivative of y with respect to x. All those mean the same thing though. So now we're going to use the limit process of the derivative to find the general formula, the derivative of f of x. We're going to find the derivative of f of x, and our answer will be a function. So it's basically that difference quotient. The only difference is instead of an a, there's an x, which just means we're finding the equation of a function instead of at a particular point. We did that in the last lesson too. We just used the letter a instead. So first things first, we're going to plug in x plus h in for the function first. So wherever there's an x, I'm going to put an x plus h. This is a longer function than we did before. And then we're going to just plug in x, which is just the function itself, all over h. Now I'm going to do some simplifying here. So I get 2x squared plus 4xh plus 2h squared minus 3x minus 3h. I'll know if I'm making a mistake. Hopefully I'm not. Because everything that doesn't have an h in it should cancel out. Because in order to cancel out with our h in the denominator, we're going to need to factor out an h. So let's make sure that happens. We have a 2x squared and a negative 2x squared, a 3x and a negative 3x. Perfect. Everything without an h did cancel out. So now I have the limit as h approaches 0. I'm going to go ahead and pull out an h as I do this. So when I pull out an h out of 4xh, I have 4x. When I pull out an h there, I have 2h. When I pull out an h there, I have minus 3. So now our h's cancel. Now I'm going to plug in 0 for h, so this becomes 0. And my answer is 4x minus 3. That means my derivative function, my original function was 2x squared minus 3x. My derivative function is 4x minus 3. We will learn a shortcut on how to do this later, but it is important to know where it comes from. So this is our definition of derivative. It's what we're going to be using for a while. Is this the same one? Oh, no, it's slightly different, but same idea. I actually think I'm just going to skip this one. Same idea. Okay, so here's an alternate form. This is what we learned last time in our last lesson. That's our difference quotient. It's basically the same thing as the derivative formula that we just practiced, the definition of the derivative. The only difference is instead of x, there's a, which means you can use this if we're trying to solve at a particular point. You're not finding the derivative of the function. You're not finding the derivative function of the function. You're finding the slope of the tangent line at a specific point. Here's another form that we can use. This one's new to us. And this is, instead of taking the limit as, remember h is that distance between 2 points, as that distance approaches 0. This is finding the limit as x approaches whatever number you're trying to plug in. So if you're trying to find the tangent line at x equals 3, that means your a is going to be 3. So let's practice using that new alternate form. I'll write it down again so you can follow along a little bit more easily. So now we are not approaching, where h is not approaching 0, x is approaching a. And it's f of x minus f of a. So the function value at x minus the function value at a all over x minus a. Change in y over change in x. At this case, our a is 1. That means we're finding the slope of the tangent line when x equals 1. So wherever there's an a, I'm going to plug in a 1. And now I'm going to actually plug this into the function. So our function is the square root of 3x plus 1. So when I plug in f of x, that's just the function. Now I'm going to plug in 1. When I plug in 1, I get the square root of 3 times 1 plus 1. The square root of 4 is 2. Over, again, our x value is 1. 1 minus, or sorry, x minus 1. We don't have to plug in anything there. It's just x minus 1. If I were to try to direct substitute the 1 at this point, we're going to get 0 over 0. So we're going to have to use what we know about limits from the last chapter and simplify this. And in this case, we're going to do that by multiplying by the conjugate. So I'm going to do this part pretty fast. My numerator is going to become 3x plus 1 minus 4. And my denominator, I'm going to have that x minus 1 there. I'm not going to multiply out the denominator. Remember, our goal is for something to cancel out. And that can't happen if I am multiplying everything out. I need to factor things down. So if I simplify my numerator, 1 plus negative 4, that's just minus 3. So I can factor that into 3 times x minus 1. So now we can see that our x minus 1s are going to cancel, which is helpful. Now that my x minus 1s have canceled, I can try direct substituting that 1 in. So my numerator is still just 3. When I substitute that 1, I get the square root of 3 plus 1 plus 2. So square root of 4 plus 2 is 4, 3/4. So recapping again, what we just found was that the derivative at a particular point, so this is not a derivative function, this is the derivative at a particular point, at 1, is 3/4. Or what that means is the slope of the tangent line at x equals 1 is 3/4. Or the instantaneous rate of change at x equals 1 is 3/4. All those mean the same thing. So let's do another one. Same idea. We're just getting more practice with it. So we have the limit. We're going to practice this new alternate form. We use the alternate form when we know what point we are calculating the derivative at. So we want to find the derivative at x equals 3. So I'm writing it down just so we remember. My brain is working faster than my fingers. Here we go. So our function is 2 over x. And we're approaching 3. So 2 over x minus 2 over 3, when we plug in 3 for x, over x minus 3. In this case, to simplify, we're going to have to multiply the numerator and denominator by a common denominator, 3x. That's what will make this the easiest. So these are all those limit rules or limit suggestions that we learned. So when I multiply everything by 3x in the numerator, I end up with 6 minus 2x. And in the denominator, I have 3x and x minus 3. Remember, we don't want to do it, multiply things out in the denominator, because our goal is for things to cancel out. So I'm going to rewrite this as negative 2x plus 6. So we can see a little bit more clearly that I can factor out a negative 2 and get x minus 3. So now these x minus 3's cancel. And now when I directly substitute the 3, I get negative 2 over 3 times 3. So the derivative at 3 is negative 2/9, which means the slope of the tangent line at 3 is negative 2/9, or the instantaneous rate of change at 3 is negative 2/9. So I'm going to do the exact same thing. We already know the answer for this is negative 2/9, but I want to show that we can use that first formula that we learned from the last lesson to find this answer as well. And you can kind of, whenever we're finding the derivative at a point, you can decide which way you would rather do it. So in this case, our a is 3. We're finding the derivative at 3. So I'm going to change those a's to 3's. And then I'm going to plug in. So first into the function, I'm going to plug in 3 plus h. So 2 over 3 plus h. Now I'm just going to plug in 3 all over h. So this time we are approaching, h is approaching 0. H being the distance between 2 points if we're finding the limit of the secant lines. So I'm going to multiply by a common denominator, which would be 3 plus h and 3. We're going to do that to the numerator and denominator. So in my numerator, I'm going to get 6 minus 2 times 3 plus h all over h. I'm just going to break that up into steps. So 6 minus 6 minus 2h over h. Well, 6 minus 6 cancel. The h's cancel. Hold on. Man, I made it all this way and now I'm doing something wrong because my denominator was not just h. It was h times 3 plus h times 3 because when we multiply, oh goodness sakes, when we multiply the numerator by something, I cannot forget to do it to the denominator as well. Here we go. So the h's cancel, and now I'm plugging in 0 for the h's that are left, but we will no longer get 0 over 0. We get a nice pretty answer here. And when we plug in 0 for 8, that one h that's left, I get 3 times 3 in the denominator, which is 9, and I have a -2 in the numerator. So both the difference quotient or that alternate form work when we're finding the derivative at a point. And then when we are finding a derivative function, we need to use the definition of derivative, which is basically the same thing as the difference quotient, but these are x's instead of a's. And that gives us a derivative function, which tells us the derivative at any point. We can just plug in the point after.